international. I'm here at the International Nanotechnology Laboratory, and INL is one of the partners in the project INFRACHIP that is bringing this webinar to you. In Project INFRACHIP, as you are already a little bit familiar with it, what we do is the providers or the partners in this project are offering access to various instruments and also technology platforms, and in particular, technology platforms related to different types of electronics. And in this particular case, the webinar series that you are joining now, this is the first webinar in the series that is related to the sensor platforms that are available for access through INFRACHIP. So I will be the host and moderator for this webinar, and our first webinar is going to be about printed electronics with a focus on printed sensors. So it will be presented by my colleague in INFRACHIP, Gregor, who comes from one of the providers. So from our Austrian partners. He's been working with them since 2008, and his main interests are in the field of printed electronics with a focus on printed sensors. In particular, he's a co-developer of a fully printed sensor technology based on electroactive polymers, something called PiezoFlex, and we're going to hear quite a bit more about it during the webinar. And in this particular case, having been involved in developing this technology platforms, since then, Gregor's focus has shifted to the business development and technology marketing to basically commercialize this platform and other technologies. So again, keep in mind that basically everything that you're going to see, so some of these, if you find certain features of these technology platforms interesting, then definitely keep in mind that you can apply for access to this technology platform through INFRACHIP. And of course, you're already familiar with the website of the INFRACHIP project. The specific so in this particular case, we're going to hear about the multi-purpose sensing with polymers and adapting sensors to specific. And we, in particular, let's say the polymer-based technology can be interesting because adapting sensors to specific challenges can be difficult. But in principle, the different polymers that are compatible with this platform offer different possibilities for, let's say, optimizing or customizing this platform for different applications. Of course, in this webinar, you're going to see basically some introduction to this technology and also some examples and some use cases of how it is both implemented and how other people have used it. And let's see, so I think people are still joining us. So again, let me reiterate that keep in mind that if you see something that you like or you think is potentially interesting, then obviously after the webinar you can already ask some questions, but also keep in mind that after you can contact INFRACHIP to see if access to some particular aspects of this technology platform would be of interest to your project. And I think with this, we can go ahead and get started, and I will hand off to Gregor.
Oh, thank you, Dimitri, for this introduction. And I think, yeah, let's get started. So within JOANNEUM Research, or within this talk and presentation, I think it's just to present JOANNEUM Research and our department materials a little bit, what we are doing, where we are located, and then just an overview of this technology with some projects and partners, and finally some use cases and demonstrators. And as mentioned, I'm representing JOANNEUM Research. So we are located in Austria. We are the second largest RTO in Austria with about 500 employees. are in federal ownership and have various locations in 7 research units. And of course, the main focus is on R&D projects, about 500 per year, national as well as in European projects. We have many publications, lectures, and of course also educating young scientists in the field of bachelor, master, and PhD thesis, and have about 71 million euro total assets and about 4 million investments per year. Quite international company, so about 18% international staff with 26 nationalities. And here you can see some figures within Horizon 2020. We had about 39 projects, and also we're quite successful now in Horizon Europe as well. And JOANNEUM Research is divided into 7 research units. It's like digital, I think it's self-explaining, information and communication technologies. I'm representing materials, so sensors, photonics, and manufacturing technologies. We have robotics, core-med, and health in the field of non-invasive and biomedicine, life, and finally policies for economic and innovation research. And so the department materials is divided in 5 research groups again, and I am representing the hybrid electronics and patterning. And JOANNEUM Research, basically, we are located in the southeast of Austria, so in the counties of Styria as the headquarter. We are also located in Styria, and within these 5 research groups, and hybrid electronics and patterning is one of them, there are 2 main focuses. One is the hybrid electronics, and one topic of the hybrid electronics is biosaflex. And the other core topic is patterning, like roll-to-roll UV nano imprinting, which might be a topic in another webinar. But today is the biosaflex technology, the focus. It's a multipurpose sensing with polymers or electroactive polymers. And so in the beginning, I'd like to give an overview. So we regard it as some major technology, or basically a technology platform based on printed electroactive polymers. And it has the ability to detect changes in pressure, temperature, vibration. And due to the piezoelectric effect, it can be used for energy harvesting as well. But all this, what is shown here, will be shown later on in the presentation within some videos or animations. But I think it's quite important that we don't only have a profound knowledge in the field of printing, but as well in the hardware design and readout electronics to design an overall sensor system. And we already have tied down the partners for high volume production. So for the upscaling of the printing ink, as well as for the printed piezo element. And so it's a quite mature technology. We are working in this field since 2008. It's based on a PhD work of a colleague who should have given this talk today, but has another appointment. And so biosaflex technology, I think, offers several technical features like the scalability, the upscaling. So you have a freedom in geometry and size due to printing. It's very flat, so you have a very low installation height. It's basically a pretty energy-friendly solution, and it can be integrated in various processes. So as an additional component, giving objects a new sensory function. And I think it's also quite important that due to current developments, it's that it can be combined, of course, with other sensors. So not only a piezoelectric sensing, but also you can also go for humidity or absolute temperature values over on one substrate. So you have a multi-purpose sensing, to name it this way. And so biosaflex itself, now some features, fabrication, and the working principle, and some other slides explaining or giving you a rough overview of what this technology means and is capable of. And so biosaflex means the sensor has the ability to detect changes in temperature. It's like bioelectricity. So for touchless interaction, proximity sensing, and all this stuff. this is currently a side topic, and we are focusing on the piezoelectricity. At low frequencies, it's the change in pressure. So for touch and HMI, so human-machine interaction, and of course, the pressure change in high frequencies, it's like structure-borne sound, which can be seen here. It's a metal trim bar of automotive. And it's like what you hear is also the sensor, can act as a microphone as well. And it's like when you drop a stone in the water and the structure-borne sound, as the sensor or the sensing device is ultra sensitive, it can easily detect any vibration. And finally, the printing itself gives us the high flexibility. So it's a flexible substrate, which gives us the third dimension, like the bending, the twisting, and all this, which in comparison to inorganic piezos like lead zirconate titanate or barium titanide oxide, yeah, it has many advantages. And I think the flexibility is one major asset of this technology, the scalability and the flexibility. And so here we see it, as I stated in the beginning, as a technology platform, which can like equip existing surfaces or existing products with new features, or provide or create new fields of use. And the main fields of application we see are in consumer electronics. But this is, as well as smart mobility, a highly competitive market. So I think to place a new technology into the market, it's like a niche technology or niche applications, which might be very well found in the field of smart city, smart living, in industrial sensing, or in health and well-being. And those are these main market segments where we intend or working to place the technology within new products. Here you can see, and I think this is unique, at least in Europe, but maybe all over the world, that due to this long time experience we have, so it's now 16 years, that we have a profound knowledge along the entire value chain. So we have knowledge in the field of design and simulation of how does the sensor need to look like, which materials do we use, like printing inks, are we going for p-dot electrodes, are we going for carbon electrodes, which substrates do we use in order to achieve a tailor-made or perfect solution for each given use case. Then we have the manufacturing in-house as well. So the printing, we can cover the electronics. So of course, the signal pre-processing, signal processing as well as communication. Then the hybrid integration to, on the one hand, add standard electronic components to the printed sensor, but also to integrate this whole system into various buildups, like into floor tiles, like on textiles or whatsoever. And finally, of course, we have the software for proper signal interpretation and visualization. And here are shown in material. So it's a Piezotech Arkema, it's a French company, which provides this PVDF TRFE ink. We have a strategic partnership over many years with them, as they are really providing excellent material, and we have an excellent partnership. And since beginning of this year, we also have acquired Armor Smart Films as a partner. It's also a French company from Nantes, which can make the upscaling of the manufacturing. So Armor is a manufacturing partner which can make high volume production of these printed piezo elements, either in sheet-to-sheet or roll-to-roll process. So they, within the year 2024, they made the transfer from a sheet-to-sheet based to a roll-to-roll based process for high volume production, also like endless designs for some specific applications. So the sensor or the core of the technology basically is, of course, the printed device. So I think most of you might or will be familiar with printing. So it's a screen printing we have various substrates like PET foils, paper, Kapton, polypropylene. I think nearby any given substrate, as we can print a primer to make it ready for printing the sensor following. And it's then the first electrode, it's like a vertical layer stack up. So it's the P.PSS, it's the bottom electrode. Then in the second step, we print the active material. So it's the PVDF TRFE ink from Arkema Piezadeh. The third step is, again, the top electrode. It's like a capacitor structure. And finally, the silver linings in order to connect the sensor to readout electronics. And if needed, we can print the protection layer on top of it. And so then after printing, here you can see just an impression that the printing really enables you this high flexibility and also nearby any structure, any design. And after the printing, this should be shown here now. Oh no, sorry, I have to slide back and start this manually. It's like a permanent magnet, so we have to carry out sort of a polling. It's we call it the deactivation. It's then also shown in the next slide that this printing material has some dipoles, and after printing they are randomly distributed. And by applying an electric field, so you can use different ways of polling. It's like contact polling, hysteresis polling, or corona polling. You insert the voltage in the electrodes. You create an electric field, and within this electric field, the dipoles are perfectly aligned in order to activate the sensor. So here you can see in the video, you increase the electric field, and by increasing this field, you give these dipoles the preferred orientation in order to make them ready for sensing or to detect these temperature pressure changes or vibrations, which is shown on the left picture here. On the top, you have this semi-crystalline material with amorphous regions, where the dipoles are randomly distributed, and by applying this electric field, you give them a preferred orientation, which then activates the sensor. And we also at JOANNEUM have an automated polling machine, which is capable of industrial standardized polling up to a size of A3, and this acts as a quality control as well. So we can track or monitor each sensor pixel for the polling current and know how well the sensor is working or how good it is working. And we have for standard geometries and standard substrates a yield of more than 99% with a very high remnant polarization up to, I think, 75 millicoulombs. And the working principle of the device is basically it's a transducer or a printed piezo element, or if you're non-physically correct, like a sensor foil. So you have an incoming physical quantity like a force, a pressure, temperature, and this transducer converts this physical quantity into an electrical signal or an electrical quantity, which is then further processed by an electronic circuit. You see in this GIF the working principle, and due to the fact that it's an piezoelectric material, we basically don't need any power supply for the transducer, so for the foil. Of course, for the readout electronics, some power supply is needed, but this effect or this piezoelectric effect also gives us the possibility or the ability to use the device for our energy harvesting applications, which will be shown later on. And I think here also shown on the bottom, the text, it's quite important to mention that it's not an off-the-shelf solution. So you don't have one solution fitting all applications or all needs, but we really have to have a clear understanding of each given use case of each problem in order to develop a tailor-made solution. Like mentioned in the beginning, to choose which design we go for, which signal conditioning we use. Of course, you need another electronic or signal processing if you have like a stiff surface, like a flooring or a table or a glass. in order when you have like a very flexible surface or with high damping like a textile. But we have comprehensive solutions in-house. And it's not only the foil sensor, the printed piezo device, where we can do the simulation, fabrication, the polling, but as well the hardware and the software, where we then have the full system integration into one demonstrator. And then finally, within iteration processes and testing, and also of how to integrate it into the final build-up, going to the prototype level. And then we hand over to our manufacturing partners in order to really make the final product and the upscaling. And yeah, here you can see that we already carried out lots of reliability tests. So it starts with the temperature storage test, down to the flammability. Those are standard tests in automotive industry, and basically, or respectively, pre-tests, and they are successfully completed. And then we did some with a partner company, some further testings. It's like the bending cycles, where you can see we carried out a 4 million with a deflection of ±1 centimeter and 2.5 million pressure loads with 9 Newton per square centimeter, which is a typical load of a finger when you touch a surface with your mobile phone or a touch screen. And we didn't see any degradation in signal. And all those tests have been carried out with non-protected sensors. So the sensors used here didn't have any printed protection layer on top. So more or less bare sensors where the sensing layer as well as the electrodes have been in contact with the fingertip or whatsoever. It was also quite a task and quite important to define this downstream management and bring the value chain in place. And so I think it's might look a bit complex, but it's pretty well working. So the R&D and the sensor design, as well as the first processes or iteration processes, are done at JOANNEUM Research. Then we have Piezotech and Amor with ink fabrication, the transducer fabrication, as well as the polling. And for the software, here it's might a bit tricky to explain, but we found out over the years that many companies approaching us and are interested in these technologies have different levels of knowledge. So some only need the sensor foil, the printed piezo element, as they can do every additional or following step in-house. So they know how signal processing works, they know how software, firmware, all this works. But some other companies really need the full assistance in like firmware, software, and the final installation into their build-ups. So we had to learn that we have to be quite flexible in this case, that each partner has specific needs, and so that we can sell the sensor foil as a product, but we can also send the full sensor system with the installation as a product. And this is basically a sketch of the workflow we carry out at JOANNEUM Research. So we roughly divide it in 2 phases. We have the phase 1. Of course, we need to have a clear idea and a clear understanding of the problem, the need or whatsoever of the customer or the partner interested in this technology. Then we have like our core competencies or key skills. It's this customized transducer design, the printing and the polling with iteration processes, and developing and adjusting the readout electronics, and ending in the proof of concept, like in a working demonstrator or whatsoever. In the second phase with iteration processes, we have then the prototype developed, installed, and then hand the process over to our manufacturing partners. So it's basically two phases with the pre-development and the final development. And I think it's quite important to mention here that, of course, over the years we have increased our knowledge, and we're starting from a totally different level as we did 10 years before. So also the bonding or to put it in another way, we have faced lots of challenges over the last couple of years. And I think we have many skilled experts in house which really contribute to a very, very well suited solution to the most various use cases. And here just some projects, demonstrators for given applications or use cases. I just want to highlight two projects, which European projects which have been using BiSoflex. One was the project Smart to Go. It finished in early 2023, and the other one is Symphony on the right-hand side, which finished a couple of months ago. You can see the project partners here, and in Smart to Go, we were able to equip a ski from Atomic with sensors, but also a whole processing platform, which you can see on the pictures on the left-hand side. So it's a supercapacitor, for example, from Tampere. It's a Bausch cell from Vata Micro Innovation. And it was a nice project demonstrator, which showed if every involved RTO company, if every involved project partner can bring in their core competency, you can really create very, very nice and working things. And it was already tested on snow, working, and Atomic further wants to develop this to really a product level. And on the right-hand side, it has been Symphony, where BiSoflex technology was the core topic of the whole project. And on the one hand, it basically dealt with energy harvesting and condition monitoring. It for wind turbines, like for smart floors, and finally also for the bicycle tube, where they want to power a tire pressure monitoring system for like professional bikers and all this, as it seems of quite an important feature, not only in tires for cars or whatsoever, but also for bicycles. And we have also been able to really achieve nice results within those two projects. And here some project demonstrators, as well an overview, and I will show later on a few more in detail. Here it's used for industrial sensing for the so-called nip measurement between two rollers in order to align the snip between these two rollers perfectly, which is really well working. On the picture below, you can also see the design. It's another design of the sensors and the flexibility that we're really able to mount those sensors around the roll. Then this here was just a demonstration for an exhibition booth where you can use it as a condition monitoring device. Here it's measuring the vibration of a coffee maker, as each process step while making a coffee, like grinding the beans and brewing and whatsoever, has a specific vibration pattern. And with machine learning algorithms, we were able to just identify the ongoing process within the coffee maker, which was quite nice for exhibition. And finally, the smart floor. Here you can see another specific design of the sensor, as well as the small black part here is a specific designed electronics in order to fit really into the buildup of each tile or floor tile, to not change I'll start it again, the buildup height. So we were able to integrate it in the final floor, and each tile has a specific code or IP address that you can really see which tile is currently activated, and it can be used in private places, for example, as a fault detection system for elderly people. It can be used as an invisible alarm system, also for smart living, like when you step on a certain tile, light will switch on or whatsoever. And in public places, it can be used for like customer journey tracking in stores or a singling of crowds or whatsoever. In the field of user interfaces here, this was also a nice outcome of a project. It's the smart card. There was the idea, this is 10 years ago, to really replace the wallet. It's like an electronic wallet where you might have different cards, like credit cards, your driving license or whatsoever. And here the sensor, which you see below, it's a 3x5, is mounted directly behind an electrophoretic display. I think this was flex enable. And yeah, here you, in this video, it's not shown, maybe in another video later on, that it's not only bending, but you also have touch and swipe, which was a nice project demonstrator as well. Another one is here, where we made a flatbed printing and then also mounting micro LEDs. And finally, it has been molded, but not injection molded, and a 3D form in order to replace some switches and buttons in automotive. Another use might be in the field of health and well-being. In this case, it was printed on a stretchable substrate on a thermoplastic polyurethane, TPU and Intexer. And we also did the app and the electronics. And here it's just shown if you do some sort of exercises the right way. And finally, here you can see the ski again. The response of the sensors to bending, like shown in this video now, as well as to the vibration, which is shown here. So the sensors basically react live or in real time. And this is to be used on the one hand for like atomic the ski manufacturer in order to get more knowledge of their manufacturing process and of the stability of the ski and each of the single layers they use, as well as the behavior of the ski on different slopes, if it's snowy and if it's icy. And of course, for the race skiers, the professional skiers, to optimize their skiing behavior, the turnaround points while carving and so on. But it's really for atomic, they really can now gain information of their behavior of the ski, which they didn't have before. So it's really an additional value for them. And so I just put together still some presentations or demonstrators in the field of different application segments, like consumer electronics, human machine interfaces in this regard. And here you can see like the showing of a plane of paper. So you can really, by programming and all this was done by Microsoft as a project partner in an European project running till 2015, that it can be used in order like for a new controller for gaming or whatsoever. Here the same animation with a different design. This is used, not really for HMI application, but it was used for movement control in the field of rehabilitation. Like if you move the elbow correctly or the knee after a surgery. This was also a nice one. So a second controller for a mobile or a smartphone. And this shows, for example, that you can really move and scroll at the same time. Again, shown here, which is, I think, as far as I'm aware, not yet solved by mobile phone producers or whatsoever. And also just as a project demonstrator showing the capability of this technology. Here we integrated the sensors as a backplane or sort of a backplane to an e-reader, where by bending you can basically switch or flip the page. So by bending it backwards, you turn to the next page. By bending it forwards, you turn to the previous page. Also with an electrophoretic or e-ink display from Flex Enable. And here on the left hand, it just simply replaced the mouse and used as a trackpad and integrated into standard PC or Windows software. And I think here again, on the right-hand side, you can see now the smart cut, so the swiping in the beginning, now the touch, and now the bending. So this combination with the electrophoretic display and BIOSOFLEX as input device worked pretty well. So here you can see that he did some sort of payment, and now he's choosing the pay method like PayPal. And what you don't see here, it's not only the PIN, but you can integrate it as an additional security feature that you track of how strong you push each button or each number of your PIN code. So it's an invisible additional security feature. So if one just gets your PIN but doesn't know the pressure, you have each of your 4-digit code activated, it won't work. So it's like a two-phase authentication, if you can put it this way. In the field of industrial sensing, now other demonstrators. Here, I'm sorry that this slide is in German, but I will translate it. I think Davisoft made it only in German, but it's sort of a brake force measurement for rail systems. And normally when you have the measurement of braking pads in rails, you have to disembark the brakes. Within maintenance, this is quite an extensive process which consumes much time, and currently they don't or are hardly able to really check the braking pressure, so between braking disc and braking pad. And we developed a solution which is shown here, which can easily, due to the flexibility, due to the low installation height and all this, be integrated between braking disc and braking pad to measure the brake force without disembarking or dismantling the brakes. And it worked really, really fine. And yeah, we are a similar system is already in the market, but we still would like to really realize the market entry by hopefully our French partners might be able to approach like French railway agency. And another one here, it's together with Bosch Rexroth, which have the so-called Arena 2036 in Stuttgart, in Germany. And one part of this Arena 2036 is like the industrial floor or of the future. I hope this slide and also the video on the right-hand side might give you an impression that Bosch sees that also production processes are changing, so that the redesign of facilities has to be done quickly, that also the amount of pieces produced is varying and also decreasing, that you might only have maybe 10 or 20 pieces of some stuff produced and then to reassemble the production line. And they have or are currently developing a sort of an industrial floor where you have many different sensors integrated. It's like one tile or one piece is 60 times 60 centimeters. And they have, for example, inductive charging. They have various pressure sensors. They have like LED stripes for these HGVs, these automated guided vehicles, where you can change the colors, for example, when they are red, the vehicles don't move. On the left picture, they are blue. Here, these vehicles move, and I think all the squares in green are then where people can move. And they have currently installed load cells, and the installation height of the load cells is quite a topic, and also the pricing as well as the spatial distribution of these load cells. So they just get basically a single signal 0 and 1. There is some activation on this specific dial or not. But we have been able to equip one tile with 16 sensors. And so basically there are 1,280 sensors integrated in 30 square meter floor. And we did this installation in 2023, I think, end of 2022. And they are currently or still evaluating and training and creating training data in order to optimize the algorithms for a further rollout of this product. But as far as we are aware, the interest of stakeholders for this development is pretty high. And of course, it's pricing is always a topic. Like also here, you might not cover the whole floor of your facility with this system, but maybe specific areas, maybe in the clean rooms, or maybe in areas where some specific high-end fabrication takes place. But it's also very nice. In the field of vital parameter monitoring, we have one partner. It's a small Austrian company, the company Pacemaker, which really integrates the sensors. I think InSole or Smart InSole is quite well known in the field of printed electronics. And there are several solutions already existing and on the market. But here, I think it's fully integrated into the Flex PCB and foamed into the inner sole. And so you don't have any external device like for transmitting or recording the data. And I think this is shown here in the video, which, yeah, just enjoy to watch. Okay, so this is one field of Smart InSole. And the other one, here are just only a few pictures where we are currently working on it within a funded project in Austria and national fund givers. It's a Smart InSole in the field of orthopedics in the order to prevent diabetes or to have a pre-screening of this diabetic foot syndrome in order to detect like a small stone in the shoe, due to the fact that people with diabetes often don't know that they don't have it and have like this small stone in the shoe, which really causes some long-lasting problems, which in several cases also leads to amputation of the foot. And so we are working on a system with a highly integrated sensor, which you can show here, directly printed on a Flex PCB of Kapton, in order to really have some system. Maybe of course it will take still some years to have it ready as a product, but to support this diabetes pre-recognition. Other fields, in the field of medical applications, the sensors can be, of course, integrated in or laminated onto textiles. We also have developed a transfer printing process. By heat press, you can laminate it on various textiles. So for wearables, you can use it like for pulse measurement, like for transpiration measurement and all this. And also we mounted it into mattresses and textiles for sleeping. And for example, have been able to really, as it's an ultra-sensitive device, recognize or detect the body motion while sleeping due to breathing and recalculate a ballictocardiogram out of it. So it can be used in the field of healthcare, of HMIs, of industrial sensing. And last but not least, I have also, I think, 2 slides for energy harvesting. This is also quite to put it this way, maybe an ancient project. I think it was running from 2013 to 2015, where we equipped a tire with sensors in order to generate energy to power a tire pressure monitoring system, a TPMS of Infineon. And it really worked. Also, the sensor design and size and geometry was not optimized when we found out the specific deformation of a tire while driving. So by optimizing the sensor, the energy output could have been much higher. But nonetheless, we have been able to really, with a constant speed at 50 kilometers per hour, to have 3 sending events within the 90 seconds. So our sensor was the energy source for this tire pressure monitoring system, and this TPMS basically every 30 seconds send it like data like pressure, temperature, and so on of the tire to the car. Okay, it was the last slide. Thank you very much.
All right. Thank you very much for this presentation. So let's see. I'm trying to see if this shows up on this interface.
Yes.
Do the people in the audience have any questions?
Yes.
Okay, yeah, I think this is my here, yeah. That was my presentation, this, yes.
All right. Any questions that you would like to ask? So I'm trying to see. I don't think that we had anything asked in the chat. All right. Well, while people are thinking, let me ask you something myself. So in the example that you showed of the brake pressure, so I guess this is measuring the pressure between the pad and the brake, right? So it's not that the sensor would actually survive a real braking like of a spinning wheel.
Of course not. No.
Right,
It's
right.
also
So
within maintenance, but
Mhm.
they can really check it here. So you have one is the braking pad, and 4 is the brake disc. And here in between is the sensor sandwiched, and of course not the spinning wheel, as it would basically burn the sensor, but it helps them to really check if the pressure when you apply the brakes in if it's transported through the pipes to the brakes itself, because I think currently there is they don't know if it really works, if the pressure applied or arrives to the brakes. And so we can verify this by using this sensor. But it's done within the maintenance process.
All right, thank you. Okay, so now we have a question in the question and answer part of the chat. So the first question is, are you developing now also other materials than TRFE for integration with polymers, some new 2D materials maybe?
Of course, we have a look at this topic due to the fact that PVDF TRFE might be critical in future due to this PFAS discussion. It's a fluorinated polymer. And on the one hand, we are working in the field of nanoparticles, and on the other hand, of course, we are looking for other biomaterials. But here, I think, as far as I'm aware, the problem is that the coefficients are not matching values needed in order to activate a proper sensing. So with nanoparticles, it works, but with other biomaterials, it's hardly possible, at least at our current knowledge. But we put lots of effort in this.
So just, I guess, kind of a naive follow-up. So does it mean that in some sense the fluorinated molecules have the stronger dipoles that are interesting for this? Okay. All right. And we have another question. So how much is the minimum power requirement for powering the tire monitoring?
Começa por ser todo em português, não é?
So for this one, I think we had this harvesting of 10.5 microwatts within 90 seconds, and that I don't know which energy was really needed in order to have the TPMS activated for a sending event. But the guy who's asking this question can drop me a line, and I can look it up and reply in a private mail.
All right. Maybe do you have a slide with your email or some contact information then?
I can type it in the chat, I think.
Yes. Okay. So if you put it in the chat, then that would be good. All right. All right. Do we have other questions? Let's see. Okay. Okay. So the next question is, what is the best substrate that can be used for a flexible sensor?
It depends on the application, of course. I think if you go for standard application, it might be heat stabilized PET. So I think it's the PET SD 505 or something in various thickness. If you have like high temperature applications, maybe also soldering for components or whatsoever, it could be Kapton. But there's, of course, also a pricing difference between those substrates.
All right. And the next question, will the ink also work with EcoFlex silicon elastomer? And what's the stretchability of the ink?
The ink or the whole sensor buildup, of course, works on a stretchable substrate where you have stretchable conductive materials like silver or carbon inks, which provide high stretchability. With this PVDF TRFE ink, you have a certain stretchability, but it's, I would say, limited to maybe 10%, as you then generate cracks, which lead to short circuit or maybe a breakdown of the sensor. To print it on silicon, is this the question, or to add silicon particles into this ink?
All right. I guess I guess this was the silicone, right? The silicone elastomer, right?
Because printing on silicone is quite tricky due to the wetting or adhesion properties of the inks. You have to, as a silicone is, I think, basically a tricky substrate to print water-based or different solvent-based materials onto. If you have a proper primer in order to prepare the silicon for printing on it, then of course you can print a sensor on top of the silicon as well.
All right. I think we've interpreted that question correctly. All right. So the other question is, what are the suitable inks other than liquid metals?
So as an electrode ink, the standard ink we use is P.BSS, which is a polymer ink, I think, well used for capacitive touch as well as for solar cells. I think it should also be pretty well known in the field of printed electronics, and it can be carbon inks. But here the topic is the bottom electrode has to be sufficiently flat in order with no like peaks or sparks or spikes or whatsoever as it's needed for this sensor layer, that you have a very smooth and homogeneous surface where you print the sensor ink on. As if this is not the case and you have like some hills and valleys in the bottom electrode, when you have like flake inks or whatsoever, or particle inks, then you can have short circuit by bowling due to the fact that you have here a thinner sensor or PVDF TRF layer like next to it, and due to the fact that we do high voltage bowling, you can create a short circuit on these places. But B-dot forms normally a very smooth layer to print on.
All right. I think that's an interesting detail. Okay, so okay, so there is a specific question if the ink is capable to do 200% and higher stretchability.
The PVDF ink itself, not. No, here we have a limited stretchability. As mentioned before, I would say maybe 10%. Of course, the electrodes and the connection lines with silver, you have stretchable silver inks and carbon inks and all this stuff, which allows for a stretchability of 100%. But the sensor pixel itself with the PVDF TRFE doesn't allow for it.
All right, thank you. Okay, so the next question is, for the flexible sensor, which process is more suitable? Spin coating, spray coating, or printing?
I would say due to the fact that we do printing, screen printing, sheet to sheet, the answer is printing. We tried, of course, currently we're working in the field of inkjet, but we also tried graver printing in the field of roll-to-roll, spray coating, dip coating, and whatsoever. As a prerequisite for the sensor having good functionality is an homogeneous and dense PVDF TRFE layer. We found out that currently printing is the process to use.
All right. I hope that this answered that question. I mean, of course, I understand that there are other researchers who are just as invested in this thing, because obviously each of these offers certain advantages for specific purposes.
Of course, but I not but. As I think if you go for spray coating or so, you might need other solvents or where the PVDF TRFE might be dissolved to have it resulting as an ink which can be spray coated. Due to the fact that for us this approach or other coating techniques are not in the focus. I don't know if Akema Piezotech are also selling these inks, or if you just can source the powder, and this is of course possible, and try to formulate your own ink in order to make it processable for other coating processes as well. So it might work. We have achieved the best results and this high yield really by printing.
All right, thank you. Okay, so the next question, in the description of the procedure, did you use any encapsulation layer at the end?
You can. So I'll try to skip up here. So when you see it's like a standard vertical printing where we have like this electrode, the active material, the electrode, and finally the connection lines, which altogether is about 15 to 20 microns at max. And of course, if needed, we print an encapsulation on top, where just only the contacts for of the silver to the next, like a cream flex or whatsoever, are left free. So we can fully shield it.
All right, thank you. The next question is, what about environmental effects on the sensor performance, parameters like humidity, temperature?
Basically, very little. So it's a very, very, very stable material. I think it has been used, for example, from NASA to adjust the sun sails or the position of solar cells within satellites. In this non-electrical phase, it's used as an inner, not encapsulation, but filling of water pipes and all this. So it's really a fluorinated polymer is really a stable material, and like humidity is, as far as we know, a topic for capacity sensing, that humidity or moisture really hinders the capacitive effect and all these, also the gloved hand, but we don't have any problems at all. So due to the fact that we go for a volume change in the material, it's highly stable on those environmental factors, but we have an upper temperature limit of 135 degrees working temperature, due to the fact, and I think this I can show here. Here you have this PVDF-TRFE molecule, and I explained that after the printing we have to carry out the poling in order to give them this preferred dipole orientation, and by exceeding 135 degrees for a certain period of time, this preferred orientation flips again and gets the statistical again. It's a reversible effect, so you can do repoling, of course, but this is due to this, it's a material intrinsic property which we have no influence on.
All right. Let's see. So I think let's give it another 30 seconds for people to think of any other questions to ask. All right. Okay. So I think we are now at the expected time for the webinar anyway. So I thank again all the people attending the webinar and obviously asking the questions. And as we have, let's see, did you put your email or some contact information in the chat?
I did, yeah.
All right. So again, just as kind of the final reminder, so this webinar was brought to you by the INFRACHIP project, and obviously to register for this webinar, you already had to have visited the INFRACHIP website and probably have seen our LinkedIn page. So again, I can encourage you to follow the LinkedIn page of the INFRACHIP project, because we put various announcements there. Again, this was the first webinar in a series, so we're going to have 3 more, basically at the same time, every week in November. So I hope that you would be interested in attending the other webinars in the series as well. And again, if you've seen something that was of interest for your projects, then definitely, again, so you can either get in touch with Gregor, or you can also contact the INFRACHIP project through the centralized contact channel, and we will, let's say, distribute the connection. Okay, will we be getting certificate for the webinar? I think we're gonna look into this because we have some lists, and we have so I think part of the challenge is going to be that because we have the list of the registered people where we have the more extended information, but in the webinar itself, we have a more, because obviously many of you appear here under screen names. So I think it may be a little bit more complicated to try to make sure that we can easily match, let's say, the people who have attended. Philippe, are we going to have?
Yes, we will have.
Yeah.
We will have access to a list of the participants who were here today at this webinar, and those are the people who will receive the certificate, right?
Right. So, yeah. Well, like I said, so it's just because obviously I noticed that some of the attendees have registered under some kind of online nicknames or short names or other names that we probably are not going to be able to match to the list. But for those that we can match on the list, then yes, it should be possible to issue the certificate.
Yes, and if in case we don't send the certificate, please send an email asking for it, because perhaps we will miss one or two because we don't have the information. Okay.
All right. Okay. Thank you very much. Again, thank you very much for attending, and I hope that you will be interested in following the rest of this series of webinars. And of course, again, thanks to Gregor for such a detailed presentation and answering the questions about all the special technical aspects of this particular technology platform.
Thank you.
Thanks to everyone, and I hope to see many of you next week. Bye bye.
Thank you.
Bye bye.